The crime scene: processes, procedures, and analysis. The role of a forensic scientist in recovering evidence from the crime scene is extensive and methodologically approached by all law enforcement officers involved. These specialists are often called SOC-Os, scenes of crime officers. They are responsible for the overall management of the crime scene, collecting eyewitness testimony, securing evidence, and ensuring the chain of continuity is reliable. There has been no cross-contamination between samples. This is notably done through the use of audit trials. Firstly, the SOCOs arrive at the scene and ensure the area is secured effectively, and bystanders are removed to guarantee a continuity chain and prevent the contamination or destruction of potential forensic evidence. For the evidence to hold up in court, SOCOs and all law enforcement coming into contact with evidence must follow stringent rules of standard, such as ISO 17025, which relates to adequate training of all law enforcement handling and storing evidence. Physical, circumstantial evidence is to be packaged accordingly, while also updating the audit trial with every step to ensure the chain of continuity is reliable in court. This audit will also be updated if the evidence is opened in another location away from the crime scene when it is repackaged after analysis, and also be logged onto online databases to ensure the evidence can be located and acquired time efficiently. Before any evidence is collected, the untampered crime scene is recorded using photos, shot video. Certain instances of circumstantial evidence can be found in crime scenes, such as impressions. Impressions vary in shape, size, and overall depth left on certain surfaces. One example of an impression normally found at a crime scene would be a shoe print. Shoes typically leave deeper set impressions on surfaces such as mud, sand, etc. Therefore, they are much easier to interpret and collect for further examination. Collections of impressions of this size are usually done using liquid substances, such as dental stone, which can be poured into the three-dimensional impression and once hardened can be lifted and packaged, audited accordingly. Shoe soles are particularly useful impressions as they can be more thoroughly analyzed in the laboratory and link a specific shoe brand to the potential culprit. The police may then request information from local international shops that sell the model of the shoe for further investigative purposes. Moreover, the specific wear and tear of the shoes will also help to establish exactly whose shoe the impression originated from. Another type of impression is formally known as latent two-dimensional impressions, or in layman's terms, fingerprints and such. These types of impressions are usually found on more rigid surfaces such as wood, tiles, glass, etc., and are much harder to lift. This is done by using specific impression powders which enhance the impression to the naked eye and also allow for the evidence to be collected and stored for later analysis. The lifting process may be done using tape, however. With technological advancements in the field, SOCOs may also be specific lifting machines to help more effectively collect latent impressions with much less risk of destruction of evidence. Also, prints may be found on items already transported to the lab, such as weapons. This can be done using a variety of chemical tests. During this collection process, officers may also be collecting direct evidence, such as eyewitness reports, if any, from neighbors, residents, and bystanders, who may have specific intel which is of use to establish the culprit and reconstruct what exactly happened at the crime scene. Additionally, with the discovery of Locard's exchange principle, law enforcement now understands that evidence may be found elsewhere. Locard's principle was founded in the early 20th century and proved that the perpetrator of a crime leaves evidence of himself being there and also takes evidence from the crime scene with him. There are many ways in which this is established in current forensic science cases, such as the collection of hairs, microfibers, glass shards, etc., which are collected in a variety of ways and stored accordingly. Firstly, hairs may be collected from the scene if located. In the instance of a deceased body found on the scene, the SOCOs will also secure a reasonable sample, usually between 30-50 hairs, from the deceased to determine whether the hairs belong to the deceased or another person. Hairs can be analyzed to determine the race, sex, and possible age of the perpetrator, along with potential DNA, assuming the root is present, being analyzed and compared through a digital police DNA database. Certain toxins may also be identified in hair, such as arsenic. Animal hairs may also be collected in the same fashion and prove vital if the deceased had no record of owning pets. Other forms of DNA evidence may be blood, saliva, semen, etc. Blood is usually seen in more violent crimes. The analysis of blood spatter can prove vital in the reconstruction of crime scenes, while also allowing for DNA to be extracted and examined in the laboratory and compared to the digital database for potential matches. Blood is also classified into certain types, which can lower the search in the event of insufficient records. Other methods of analysis can be done involving toxicology to determine the cause of death in cases of potential murder. As mentioned, toxins can be present in extremities such as fingernails, hair, etc. Alternative sources of trace evidence may be found in different scenarios. One example may be glass in a burglary or perhaps a vehicle accident. Glass fragments can be very specific in shape, density, and refractive measurements. Also, depending on the function of the particular glass pane, the glass may act differently. For instance, window panes are much less resilient as opposed to a car windshield, and thus smash into much larger fragments with much less force needed, whereas the windshield of a car is laminated and the glass itself is tempered to separate into much smaller fragments. Upon further forensic analysis, scientists can determine vital information such as glass manufacturers and local dealers who may have sold panes like this recently. Following Locard's principle, it is highly likely the perpetrator has fragments of glass on his person as a result. It is usually said that the evidence will have been shed within 24 hours, as by then the offender will likely have changed or disposed of clothes. The same can be said for a car's paint. Paint is another form of useful trace evidence, and when collected, can be analyzed the same as the glass of a car, which can even link to a specific model of a car if the paint job is specific to said car model. Additionally, soil samples may be found in a car or any crime scene, and soil samples are very useful for determining the geographical location in which the perpetrator resides. These samples may be collected using a specialized hoover, while also packaging the nozzle as evidence appropriately. Referring back to Locard's principle, soil samples of the same composition may be found on the offender or in the offender's residence, linking them to the crime. With all of the circumstantial and direct evidence combined, forensic analysts can begin to reconstruct the sequence of events that took place at the crime scene. With the innovation of technology, document forgery has become much more commonplace, alongside the difficulties of establishing a forged document from a genuine one. However, forensic scientists have innovated ways to figure out the truth. The most common types of forged documents range from banknotes, passports, etc., and these may be forged digitally or by hand. There is a large variety of methods used to print forged documents, such as screening, lithography, etc. Handwriting analysis focuses on the characteristics of the author's writing, looking for inconsistencies in the length of letters, the spacing, and any missed grammar. Whereas there aren't observable anomalies within digitally forged documents, the materials themselves can show inconsistency. The testing begins with non-destructive methods, such as infrared microscopy. If this method fails, destructive methods are used which involves the ink on a page being separated and observed in much higher detail with the use of chromatography, which will also help establish the use of multiple ink types or destruction fluids to remove words. This is only done after recording the original document, as ink is required from the document for the process to work. The paper itself may be analyzed to determine whether it is from the same manufacturer and whether they share the same age. Observable inconsistencies such as the final coating of paper, the fibers used to make the paper, and the types of treatments used can prove vital in the identification of falsified documents.